according to National Electrical Code Section 250.96, where metal enclosures for electrical equipment are connected to a grounded raceway, all metal enclosures shall be connected to the raceway by means of an equipment grounding conductor. This requirement applies to motor disconnects. Based on the description provided, the rigid metal conduit, or RMC, entering the motor disconnects appears to be connected to the raceway system containing the equipment grounding conductor. Therefore, a bonding jumper is required to connect the RMC to the equipment grounding conductor within the motor disconnects. National Electrical Code Section 250.97b states that enclosures such as motor disconnects that are not listed as suitable for grounding shall be grounded by an equipment grounding conductor that is run with and connected to all phase conductors. The disconnect is not marked as suitable for grounding. However, it is not clear whether the disconnect is supplying a grounded or ungrounded system. If the system is grounded, the disconnect requires an equipment grounding conductor regardless of its suitability for grounding. The provided wiring configuration does not appear to be fully compliant with National Electrical Code Sections 250.96 and 250.97 as follows. Firstly, a bonding jumper is missing at the RMC entry point of the motor disconnect. Secondly, it is unclear whether the motor disconnect is suitable for grounding, and whether an equipment grounding conductor is present if the system is grounded. And thirdly, the equipment grounding conductor configuration appears complex and potentially hazardous. Here are some recommendations. Firstly, install bonding jumpers between the RMC and the equipment grounding conductor at the entry point of the motor disconnects. Secondly, verify the grounding suitability of the motor disconnects and provide an equipment grounding conductor if necessary based on the system grounding configuration. And thirdly, review and simplify the equipment grounding conductor configuration to ensure proper grounding and safety. Consider the following points regarding equipment grounding conductors and bonding jumpers. Firstly, the purpose of an equipment grounding conductor is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. This ensures that a ground fault is quickly cleared, minimizing the risk of electrical shock or fire. Secondly, a bonding jumper is a conductor used to connect metal parts of an electrical system to ensure electrical continuity and conductivity. This is particularly important in situations where the raceway system, such as RMC, is used as the equipment grounding path. The bonding jumper ensures that all metal parts are at the same electrical potential, reducing the risk of voltage differences that could cause a shock hazard. Thirdly, when installing bonding jumpers, ensure they are properly sized according to the National Electrical Code Table 250.102-R250.66, depending on the application, based on the size of the ungrounded conductors. The jumper should be securely connected to the metal parts using listed connectors or methods to ensure a reliable electrical connection. Fourthly, when evaluating the suitability of a motor disconnect for grounding, check the manufacturer's markings or specifications. If the disconnect is marked as suitable for grounding, it means it has been tested and listed to provide a reliable ground connection. If it is not marked as such, it should be assumed that it is not suitable, and a separate equipment grounding conductor must be run with the circuit conductors to provide the grounding path. Fifthly, in situations where multiple equipment grounding conductors are present, avoid creating complex or redundant grounding paths. The goal is to provide a clear and direct path for fault current to return to the source. Complex configurations can sometimes create impedance imbalances or circulating currents, which can reduce the effectiveness of the grounding system. Sixthly, when working with variable frequency drives, or VFDs, it is particularly important to ensure proper grounding due to the potential for harmonic currents and electrical noise. The equipment grounding conductor for a VFD should be sized appropriately to handle these additional currents, and care should be taken to minimize ground loops and other potential grounding issues. Consider the implications of National Electrical Code Section 250.130c when dealing with replacement of grounding conductors in existing installations. Seventhly, always refer to the latest edition of the National Electrical Code and consult with a qualified electrical professional to ensure compliance with all applicable requirements. Electrical codes and standards are subject to change, and it is important to stay up to date to ensure safe and compliant electrical installations. Eighthly, regularly inspect and test the grounding system to verify its effectiveness. This can include visual inspections of connections, as well as electrical tests to measure ground impedance and continuity. Any issues identified during these inspections should be promptly addressed to maintain the integrity of the grounding system. Ninthly, documentation is very important. Keep records of all grounding system components, including the size and type of conductors, the location of bonding jumpers, and the results of any inspections or tests. This documentation can be helpful for troubleshooting purposes and for demonstrating compliance with electrical codes and standards. Tenthly, consider the use of supplemental grounding electrodes, such as ground rods or ground plates, to improve the overall effectiveness of the grounding system. These electrodes can help to reduce ground impedance and provide an additional path for fault current to return to the source. 11thly, be aware of the potential for corrosion in grounding system components, particularly in damp or corrosive environments. Use corrosion-resistant materials and coatings to protect against corrosion, and regularly inspect components for signs of corrosion. 12thly, in industrial settings, consider the use of isolated grounding systems for sensitive electronic equipment to minimize the effects of electrical noise and interference. Isolated grounding systems provide a separate grounding path for this equipment, preventing noise currents from circulating through the normal grounding system. 13thly, when installing grounding conductors and bonding jumpers, follow the manufacturer's instructions and use the proper tools and techniques to ensure a secure and reliable connection. This can include using torque wrenches to tighten connections to the specified torque value, and using appropriate crimping tools for terminating conductors. 14thly, consider the use of exothermic welding for making permanent grounding connections, particularly in situations where a high level of reliability is required. Exothermic welding creates a molecular bond between the conductors, providing a corrosion-resistant and highly conductive connection. 15thly, when designing a grounding system, consider the potential for future expansion or modification. The grounding system should be designed to accommodate these changes without compromising its effectiveness. 16thly, be aware of the potential for stray voltage in grounding systems, particularly in agricultural settings. Stray voltage can be caused by a variety of factors, including improper grounding, unbalanced loads, and faulty equipment. It is important to identify and mitigate stray voltage to prevent harm to animals and humans. 17thly, consider the use of ground fault circuit interrupters, or GFCIs, to provide additional protection against electrical shock. GFCIs can detect small imbalances in current and quickly de-energize the circuit, preventing serious injury or death. 18thly, be aware of the potential for lightning strikes and the need for lightning protection systems. Lightning protection systems provide a path for lightning current to safely discharge to ground, protecting buildings and equipment from damage. 19thly, when working with underground grounding systems, be aware of the potential for soil conditions to affect the effectiveness of the grounding system. Soil resistivity can vary significantly depending on factors such as moisture content, temperature, and mineral composition. It is important to consider these factors when designing and installing underground grounding systems. 20thly, consider the use of surge protective devices, or SPDs, to protect sensitive electronic equipment from voltage surges caused by lightning or other electrical disturbances. SPD can divert surge current to ground, preventing damage to equipment. 21st, remember that grounding and bonding are essential for electrical safety. Proper grounding and bonding practices help to ensure that electrical systems are safe for both people and property. Grounding is a critical aspect of electrical safety and compliance. A well-designed and properly installed grounding system is essential for protecting people and equipment from electrical hazards. It's important to stay informed about the latest codes and standards, and to work with qualified electrical professionals to ensure that your grounding system is safe and effective. 22nd, the equipment grounding conductor provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. 23rd, bonding ensures electrical continuity and conductivity between metal parts, reducing the risk of voltage differences. 24th, always use appropriately sized bonding jumpers, securely connected with listed connectors. 25th, assess the grounding suitability of equipment, using separate equipment grounding conductors if necessary. 26th, avoid complex or redundant grounding paths, maintain clear and direct routes for fault current. 27th, give special attention to grounding VFD to manage harmonic currents and electrical noise effectively. 28th, remember to consult the latest NEC edition and seek advice from qualified professionals for code compliance. 29th, conduct regular inspections and tests to ensure the grounding system's continued effectiveness. 30th, maintain detailed documentation of all grounding system components and inspections. 31st, when necessary, consider the use of supplemental grounding electrodes to enhance system performance. 32nd, use corrosion-resistant materials to protect grounding components, especially in harsh environments. 33rd, deploy isolated grounding systems for sensitive electronics to minimize electrical noise. 34th, adhere to manufacturer's instructions when installing grounding conductors and bonding jumpers. 35th, consider isothermic welding for highly reliable, permanent grounding connections. 36th, always plan grounding systems to accommodate future modifications or expansions. 37th, stay alert for stray voltage, particularly in agricultural settings, and implement appropriate mitigation strategies. 38th, use GFCI protection to minimize the risk of electrical shock. 39th, ensure proper lightning protection systems are installed to safeguard against lightning strikes. 40th, factor in soil conditions when designing underground grounding systems. 41st, protect sensitive equipment with SPD to guard against voltage surges. Properly designed and maintained grounding systems are crucial for electrical safety, preventing hazards, and ensuring system reliability.